Let us extend the discussion here that we stopped in the last session here, right? So let us look at now. V is inversely proportional to C, then V1 can be written as C2 by C1 plus C2 into total voltage V, and V2 is equal to C1 by C1 plus C2 into total voltage V. You call it voltage division rule. In case of capacitors, voltage division rule you can write like that. But when there are, okay, similarly, voltage across kth element, when there are n number of capacitors connected in series. So what you get here, V is inversely proportional to C, therefore 1 by Ck by summation I is equal to 1 to N, 1 by Ci, yes or no, all of you, okay, into total voltage V. This is the voltage across kth capacitor when n number of capacitors are connected in series. You have to remember this formula because in exam sometimes he may give you more than 2 capacitors. So you cannot really take a chance to simplify 2 capacitors first, then again the resultant with another capacitor. Not like that. It will take a lot of time. Unnecessarily don't waste your time. Remember this formula. Voltage across kth capacitor when n number of capacitors are connected in series. Understand all of you, okay? Now it is also very clear, V1, it is 1 by C1 by 1 by C1 plus 1 by C2. After simplifying that, you got C2 by C1 plus C2. Okay, I have directly written, but it is, coming from this particular one only, 1 by C1 by 1 by C1 plus 1 by C2. Simplify it, you will get the same value. Similarly, this one also. Okay. So in series combination, the charge same, but voltage divides. This is the voltage across kth capacitor when n number of capacitors are connected in series. It's more generalized formula. It's very, very important. So what will happen when the capacitors are connected in series? The effective capacitance will decrease or increase? Less than even the lowest value of all these capacitors. The effective capacitance is less than even the lowest value of all these capacitors. Now, second one is a parallel combination. Okay, voltage same, but the charge divides. Voltage same, but charge divides. Okay, yes or no? Look at this. Now, 2 capacitors connected in parallel. We'll generalize it for n number of capacitors later. This is the voltage and the charge supplied by the capacitor. Okay, it divides into Q1 and Q2. But voltage is same, yes or no? Voltage is same. This is V and this is also V. There is no change here. Understand all of you, okay? Here, you must understand, always there is a charge conservation at every node. Just like KCL says, algebraic sum of the currents entering into node is 0. Yes or no, all of you? Similarly, the charge at a particular node must be conserved. That means the charge total supplied and charge total absorbed must be 0 at every node. Look at this here. If you take in the series combination, if you take, this is what the charge supplied by the source and this is the charge deposited on conducting plate of this capacitor. This is the node. What is supplied? Q. What is absorbed? Q. Therefore, the charge is conserved. Supplied is equal to absorbed. If supplied is plus and absorbed is minus, then algebraic sum will become 0. Similarly, here also. Understand all of you, okay? What will happen here? This is plus, this is minus, and this is plus, this is minus. Yes or no, all of you? Now here, this is minus, this is plus, but the net charge is becoming what? 0 again. Understand all of you, okay? Because charge, this is plus Q, this is minus Q, this is plus Q, this is minus Q. Yes or no, all of you? So what is happening here? This is, here it is supplying the charge, here it is absorbing the charge, the net charge is becoming 0. But when it comes to the capacitors here, what is happening? This is minus Q, this is plus Q, but the net capacitance will become, net charge will become what? 0. Similarly, This is absorbed and this is supplying, and at this node the net charge becomes 0. At every node the charge must be conserved. It's very, very important. Understand all of you? Okay. Now here also the total charge is Q and the total charge absorbed by the two capacitors is Q1 and Q2. Therefore Q1 plus Q2 is nothing but Q here, or Q is nothing but Q1 plus Q2. And KVL as usually, V and minus V0, V and minus V0, that's it. KVL is always satisfied. At every node KCL must be satisfied. Okay, in every loop KVL must be satisfied. Understand all of you? Okay. Now this is A, this is B. Let us assume CAB will become C1 plus C2 plus and so on Cn. Finally, I can write it as what? Summation I is equal to 1 to N Ci. CAB can be written like this. Understand all of you? Now the CAB is greater than even the highest value of C1 and so on Cn. Even the highest value of C1 and so on Cn. Understand all of you? Okay. N is equal to 2. Obviously, CAB will become a simple one, that C1 plus C2 for a parallel combination. Now you can write, okay, Q1 is equal to C into V1, C1 into V, okay, and Q2 is equal to C2 into V. From this we can write Q is directly proportional to C. But Q also, you know very well, charge gets divided Q1 plus Q2. Finally, based on this, Q1 can be written as C1 by C1 plus C2 into Q. And here Q2 can be written as C2 by C1 plus C2 into Q. Kth capacitor charge can be written as Ck by summation I is equal to 1 to N Ci into Q. This is the generalized expression that you can take the the charge deposited on kth capacitor when n number of capacitors are connected in parallel. Understand all of you? Okay. So this is called charge division rule. Charge division rule. Understand all of you? Okay. So please note down this quickly, all of you. Note down that. This is what series and parallel combination of capacitors. You have seen resistor and conductance formulas in the beginning of the classes, okay? In the very beginning classes. All conductance formulas and capacitor formulas look same. They look similar. They look similar. All resistor formulas, inductor formulas look similar. Now, similarly, you can apply for star delta transformation also, because in the exam, you are getting some questions on star delta transformation also. Okay. Delta to star. CAB, CBC, CCA, CA, CB, CC. CA can be written as CAB into CBC plus CBC into CCA plus CCA into CAB by CBC. CB can be written as numerator same CCA. CC can be written as numerator same CAB. Okay, just like conductance formulas looks like. You can go back to your conductance formula. Very beginning we have studied this in the started transformation. You can also cross check. Fourth one is star to delta. Hope you have written all these things right. So please proceed with that. Meanwhile, I just write the formula for star to delta transformation. CAB can be written here, CA into CB by CA plus CB plus CC. CBC can be written as CB into CC by CA plus CB plus CC. CCA can be written as CC into CA by denominator same. This denominator is same, right? So let me write just simply bracket so that you remember the denominator is same here. If, note, if CAB is equal to CBC is equal to CCA is equal to C delta, CA is equal to CB is equal to CC is equal to C star. Okay, you can write here from this, it is C delta, right? C delta can be written as, okay, what is this? C star square by 3 times C star, C star gets cancelled. Finally, C star by 3 you are getting. Or else, C star can be written as 3 times C delta. It is very clear that each element of star equivalent will be 3 times, okay, the delta equivalent capacitance. Okay, delta equivalent element. Each element of the star equivalent of capacitor, the star equivalent of the capacitors is equal to 3 times the element value of delta equivalent circuit. Yes or no? So it's very clear, we observed very clearly. So please quickly complete them. Then we can switch over to the topic. So we have seen series, parallel combination, voltage division, charge division, yes or no, star delta transformation, all are very important. You are going to use these formulas in solving the problems also. So next important one is what? Inductors. So once you understand the capacitors, you can also understand easily the inductors. In the similar flow, you can go and complete all those, okay? First, we write certain points about inductors. Please write down. It's a passive element. Please write down. It's a passive element. It's a passive element that stores energy in its magnetic field. Yes or no, all of you? In its magnetic field. Okay. Write down one more important point, that, okay, how inductor is formed. Let us try to understand. A simple point you can write. Write down that point. Any current carrying conductor, conducting wire, any current carrying conducting wire, any current carrying conducting wire can be regarded as, any current carrying conducting wire can be regarded as an inductor. Okay, I think all of you understand the point. If you take current conducting wire, what will happen? When current is passing through any conducting wire, the flux is produced. Yes or no? The produced flux will be established around the conducting wire in the circular loops. You might be knowing according to Ampere's law. Any current carrying conducting wire will produce the flux, and that flux will be established around the conducting wire in the circular loops. Understand all of you, okay? Now you can find what is the intensity of that flux, okay? What is the flux density, what is the intensity, all those things, that's a different story again. Okay, right hand thumb rule can be used even to identify that direction of the current and direction of flux. Suppose you have, let us say this is a conducting wire, then you catch the, this one, this particular conducting wire with the right hand. Now this thumb indicates the current and the fingers are representing what? The flux. Yes or no, all of you, okay? Now, write down the point. In order to enhance, in order to enhance the flux, in order to enhance the flux density, in order to enhance the flux density, the conducting wire is formed into, the conducting wire is formed into, the conducting wire is formed into cylindrical coil, can be formed into cylindrical coil. Okay, cylindrical coil. So it's something like this. You have so what you're trying to do here, you're taking the wire and forming into a cylindrical coil. Okay, so thereby you're forming an inductor. Now this is nothing but the core. Okay, a magnetic core you can use. That core might be anything here. Understand all of you? Okay, air core, it might be iron core, it might be anything, it might be. Okay, depends on the requirement, we go for the core, and that is the special design, how we design the core and all, the special topic that is. Okay, so now the inductor can be represented something like this. This is representing the core, and this is representing the flux linking with the inductor. Okay, now this is what actually the current flowing to. This is flux, and this is current through the inductor, and this is what, let us say, voltage across the inductor, VL of T. And the number of turns N, and the inductance is called L. Okay, this is the standard representation of an inductor. Okay, now let us look at the phi is directly proportional to I. Yes or no? Phi of T is directly proportional to I of T. When you remove that proportionality, L into I of T. Differentiate on both sides again. D phi by dt. What is d phi by dt? D phi by dt is nothing but what? D phi by dt is nothing but what? Time rate of change of flux is always called as what? EMF. EMF or voltage. So therefore, we can say voltage across the inductor, that is, let us say IL of T, okay? IL of T, then VL of T is equal to L into DIL of T by dt. Understand all of you, okay? Can I say this is nothing but L into slope of IL of T? Yes or no? Slope of IL of T. It's very, very important. Now applying the integration on both sides, you know very well, okay? This is nothing but L into slope of IL of T. Now what do you get here? Just like in the case of capacitor, can I write directly here? IL of T naught plus integral 1 by L T naught to T VL of T dt. This is nothing but initial current. Yes or no? Initial current. This is nothing but initial current. Now initial current plus 1 by L area under VL of t between the boundaries, that is T naught to T. Okay, it's very, very important expression. Okay, now you got voltage and current relationship here, and then we go for power. What is PL of T? Instantaneous power, instantaneous voltage into instantaneous current. It's nothing but, what do you get? L d IL of T by dt into IL of T. What is the energy? WL of T. You know that already. WL of T naught, initial energy plus integration T naught to T, P of T dt, PL of T. Okay. Now what do you get here? WL of T naught plus integral T naught to T. Please proceed. Okay, you can do that easily. Please proceed. Please proceed. I'm just deriving here. Okay, L d IL of T by dt into IL of T dt. Dt dt gets cancelled. I'm just writing everything here. Okay, I'm just continuing here. All of you please proceed. From this, WL of T can be written as WL of T naught plus half. Why half? Because I di is nothing but I square by 2 after integration. So L IL of T whole square over the limits T naught to T. Okay, plus half L into IL of T square minus IL of T naught square. Yes or no? Now if WL of T naught is 0, then WL of T will become half L IL of T square minus IL of T naught square. Okay. If again IL of T naught is 0, because initial current sometimes it may be 0. But remember, always you should write the formula along with all initial energy as well as initial current. Then only, there is a possibility, because sometimes in the exam he is trying to give the questions on okay, based on this initial current and initial energy. Okay, therefore WL of T can be written as half L of T whole square. This is very, very important. Important formulas. Initial energy stored in inductor. Okay, initial energy stored in the inductor. So this is how you can proceed. Please note down that. Please note down that. And then we can, after that, you can come back here, important characteristics of an inductor. Important characteristics of an inductor. I think you have written that, all of you. Come back here. First important characteristic. Write down the point. First point. First characteristic. An inductor is short circuit to DC. An inductor is short circuit to DC. An inductor is short circuit to DC. Okay, it's very clear from this. VL of t is equal to L into dIL of t by dt. If IL of t is DC, let us say, then what will happen? Time rate of change of this constant, DC is nothing but constant. VL of t will become 0. 0 is nothing but what? Voltage 0 refers to what? Short circuit. DC is nothing but what? Frequency 0. That is nothing but what? Low frequency. Okay, DC is nothing but frequency 0. That is nothing but low frequency. That is why we can write here the inductor. What is doing here actually? Short circuit means what? Passing. Yes or no? The signal is passing now. Low frequency signal is passing. The inductor passes low frequency signal. Low frequency signals and blocks what is that? High frequency signals. It's very, very important, and based on this point and the capacitor also we discussed in the earlier session, based on these two important points, the inductors and capacitors are widely used in filters. They are widely used in filters. They are widely used in filters. So the most important characteristics which is very, very useful in case of transient analysis. Okay? In case of transient analysis. Second point. What is the second point? Please write down. The current through the inductor. What did you write in the case of capacitor? The voltage across the capacitor may not change instantaneously. Charge is directly proportional to voltage. Therefore, charge deposited on conducting plate of the capacitor may not change instantaneously. Now here the flux is directly proportional to current. So therefore, the current through can be replaced by the flux linking with. Flux linking with. The current through inductor, that means the flux linking with the inductor, understand all of you, okay? May not change. May not change instantaneously, abruptly. Understand all of you, okay? Or suddenly. We discussed already these points. There is no need to elaborate again. Instantaneously, abruptly, or suddenly. Okay? We'll prove it, how it is going to happen. Okay? So V is equal to VL of t is equal to, okay, L d IL of t by dt. Now let me write L into IL2 minus IL1 by T2 minus T1. Just like in the case of capacitors, can I write the expression like this or not? There we have written IC of t is equal to C dVc of t by dt. Yes or no? Similarly, we can write here. Now, since we are trying to change instantaneously or abruptly here, the denominator can be taken as 0. Now, our intention is to change the current through the inductor, let us say 2 amperes to some 5 amperes. What will happen? what will happen? This entire component looks like infinity, yes or no? Okay, that means what? The current through the inductor, if you want to change from one value, that is initial value 2 amperes to some other value in zero time, you require voltage across the inductor to maintain how much? Infinite voltage in zero time. You call it ideal impulse voltage. Understand all of you? Okay, that means if you are able to give that ideal impulse voltage across the inductor, it is possible to change current through the capacitor from one value to other instantaneously, but which is practically impossible. Yes or no, all of you? Okay, which is practically impossible. Ideally possible, but practically impossible. So students, you can write here now. Please note down this quickly, and then I'll give you an important point here. Okay, so please write down quickly here. Please write down quickly here. Write down quickly. After this, I'll give you an important point. From the above expression, it can be understood that from the above expression, it can be understood that to change current through the inductor from one value to other, it can be understood that to change current through the inductor from one value to other in zero time, the voltage across the inductor required is infinite. You understand? The voltage across the inductor required is infinite. In bracket, you can write ideal impulse. In bracket, you can write ideal impulse. Close the bracket and continue, which is practically impossible. Even if you, I think you have written that particular statement as it is in the case of capacitor also, which is practically impossible. If not, you please write there also. Okay. From the above expression, it can be understood that to change current to the inductor from one value to other in zero time, the voltage across the inductor required is infinite. That's nothing but what? In bracket you are written ideal impulse. Close the bracket, continuation, which is practically impossible. I hope you understand the point. Okay. Now, note, it's a very important point. These are all very, very important. I'm telling you the characteristics of the inductor and capacitor, particularly the second characteristic here in inductor, and there we have seen the capacitor also. Very important points. So the first one, this is what the inductor, right? The flux, right? Okay, L, and this is IL of t, and this is VL of t. Okay, the first point, if VL of t is finite, you understand all of you? Then IL of t may not change instantaneously. Second point, if VL of t is infinite, nothing but ideal impulse, then IL of t may change instantaneously. Understand all of you? Okay, this is very, very important point here. May change instantaneously, may not change instantaneously. That's why we do not know what is the background of that voltage, whether it is finite or infinite. That is why carefully we are giving a statement that may not change. Okay, but voltage across the capacitor may change instantaneously. Okay, Voltage across the capacitor may change instantaneously. You remember, I think all of you, in case of capacitor and inductor, in case of capacitor, we have written current through capacitor may change instantaneously. Voltage across the inductor may change instantaneously. Why we are writing again may? Why we should not write cannot or does not or will not? Reason is, sometimes the circuit is given like this: inductor and capacitor in series, inductor and capacitor in parallel. Now you see what's happening. You will clearly understand with this particular example. Okay. See, now here, since both are in series, when current is passing here I of t, since both are parallel, you know that in the parallel combination voltage is same. Here current is same, here voltage is same. What's happening here? We know that the individual statements, when you see, current through the inductor may not change instantaneously, current through the capacitor may change instantaneously. You cannot use the word current through the capacitor cannot change instantaneously, because sometimes the capacitor might be in series with the inductor. Now it has to follow the inductor only. It has to follow the inductor only. Understand all of you? Okay? Because in case of inductor, current through inductor may not change instantaneously. Since capacitor is in series with the inductor, now in this particular case, the current through the capacitor also may not change instantaneously. That is why may not is a very sensitive word that you are supposed to use very carefully. Okay, you cannot use all the time cannot, will not, shall not, does not, like that. Understand all of you? Okay. Well, here also same. You see, the voltage across the capacitor may not change, but voltage across the inductor may change. Individual statements. But when they are connected in parallel, now which statement you are supposed to take here? Now inductor is supposed to follow the capacitor. If the voltage across the capacitor may not change, now in this particular context, in the parallel combination, the voltage across the inductor also may not change. That is why I am carefully writing without the presence of any capacitor parallel. Okay, I can say voltage across the inductor may change. But in case if a capacitor is there in parallel, then it may not change. Similarly, here also, current through capacitor usually may change, but if it is there in series with inductor, it may not change. So you must be very careful here. Okay. So in case of series combination, the elements must follow the inductor if there is an inductor. In case of parallel combination, okay, the elements must follow the capacitor in case if there is a capacitor. Hope you understand the point. When the elements are connected in series, all elements must follow the inductor. Okay, what is the statement you have in inductor? For the inductor, the same statement is applicable to all remaining elements. Okay, in case if there is an inductor. Similarly, if the elements are connected in parallel, if there is a capacitor, okay, all remaining elements must follow the capacitor statement only. This is very, very important point and valid point. Understand all of you? Okay, well. So this is what actually the important characteristics. I'll take some examples here again, just like in the case of capacitor. We'll see some examples here. So please write down here, not only current, but the same statement is applicable to what? Flux. Flux. Okay. Flux linking with inductor. Some examples we are seeing here. Okay. Which of the following is or are acceptable? IL of t, a discontinuous current plus 10 amperes minus 2 amperes. Discontinuous. Yes or no? Discontinuous current may not be acceptable to the inductor. Yes or no? May not be acceptable to the inductor. Therefore, cross. Yes or no, all of you? Current through the inductor may not change instantaneously. He did not mention whether the inductor is experiencing finite voltage or infinite voltage. By default, I told you, you must take always finite only. Yes or no, all of you? Therefore, may not be acceptable because here the current is changing instantaneously. Second point or second example, you have something like this. Some current is flowing like this. Is it continuous or discontinuous? Yes, it is continuous. Yes or no? It is T1, it is T2, it is I1, it is I2. I2 minus I1 by T2 minus T1. There is no problem. But here what's happening, this is I1, this is I2, this is T1, this is T2, T1, T2 minus 0 it is coming out. So this is the discontinuous or discrete, this is the continuous. Understand all of you, okay? So this is acceptable because continuous current, okay, continuous current may be acceptable to the inductor. Please write down to the inductor. But the same discontinuous voltage across the inductor may be acceptable. Yes or no? Suppose if the voltage is given across the inductor, which is of continuous discontinuous form, some 10 volts and minus 2 volts, then what will happen here? This is acceptable because for voltage there is no problem. We have written voltage may change instantaneously. So discontinuous voltage may be acceptable to inductor. Discontinuous voltage may be acceptable to the inductor because it may change instantaneously, therefore it may be acceptable to the inductor. These are all very, very important points and important examples. If you are very good in concepts, you can answer any question that you come across. So we are trying to cover all the concepts in 360 degrees without leaving even a single point. Okay? Because tomorrow in the exam, the question may come in any direction or in any dimension. So if you really follow these kind of concepts, you can surely attempt any question that you come across. Understand? Write down quickly, all of you. We will switch over to another point. Third important point, third important characteristic. An ideal inductor does not dissipate energy. Okay, that means what? There is no resistive component. A real inductor or a practical inductor, a real or a practical inductor dissipates energy. Yes or no? Dissipates energy. A real inductor or a practical inductor dissipates energy. Okay? And it can be represented by series modeling resistor. Series modeling resistor. It can be represented by series modeling resistor. So this is what actually the practical inductor. Usually choke coil can be taken as practical inductor. I think all of you are aware choke coil. Even you might have done some experiments in the lab. Separation of choke coil parameters might be an experiment. Okay. The resistance value is very, very smaller. You can represent with the series modeling. Now this is what ideal inductor. This is a resistance very smaller value, very smaller value. So that's why you can neglect it. Smaller value in series, then the voltage across that smaller resistance will also be very smaller. So we can neglect it in most of the practical, calculations. We neglect it, but still it is there actually. Okay. There is a task actually can be asked in many of the interviews, or sometimes the problems may come in different dimension in the exam. That how to separate the choke coil parameters. How to separate choke coil parameters. Okay. So just write on the procedure, put the heading, separation of choke coil parameters. Separation of choke coil parameters. Separation of choke coil parameters. Put the heading, separation of choke coil parameters. Separation of choke coil parameters. Step 1. Apply DC. So what will happen when you apply DC? Yes, the inductor is acting like what? Short circuit. But this is a lower resistance value. So current is very high. It flows. Therefore, better you connect one rheostat in series with this. One rheostat you are connecting, and connecting one DC source across it. Understand all of you? Okay. Now when you apply DC voltage V, okay, and connect now a voltmeter and an ammeter in series with the coil, then what will happen? The ratio of voltage to current, the small r, will become what? Why you kept the rheostat here? To limit the current, because the smaller value, obviously all of a sudden some highest current flows, then choke coil will get damaged. So voltmeter reading by ammeter reading. That's it. Now step 2. Apply AC. What will happen? For AC sinusoidal, whenever you apply, you also note on the frequency omega or F. Now connect a voltmeter which reads RMS voltage magnitude. Yes or no? RMS voltage magnitude. MI type. Here you are using MI type meter. Here you are using MC type meter. Yes or no? So you calculate now the Z value, nothing but voltmeter reading by ammeter reading. RMS voltage by RMS current will give you a Z value. Once you know Z, you can calculate what is XL, nothing but Z square minus R square. And once you know XL, you can find omega is nothing but XL by, L is nothing but, XL by omega. So you got now here both R and L value. This is how you are separating the choke coil parameters. You are able to calculate both R and L values. Please note down all of you. It's a simple experiment. Choke coil parameters. What are you trying to do here? First you are giving DC, then you are giving AC.